Okay. Apologies for being extremely late. I had to get a shower, and it ran a little bit longer than I was expecting. And then I had to take care of a few other things. But we're here. We're here. And this is what we're doing right here. We're going to do Jeremy's Tech Lab, or IT Lab, Ethernet LAN switching part 2. Thank you for anybody and everybody who came and hung out with the stream yesterday for High on Life 2. I'm not going to lie, I was a little disappointed in the game. It was not nearly as cool as or fun as the first one. But that's okay. We played through a little bit of it anyway. I don't know if we'll continue it or not. But anyway, we're going to watch this. We are going to do the packet tracer. And then we might do the Anki flashcards as well. But I do have somewhere I need to be later. So we're going to kind of just go ahead and dive straight into it. Of course, if you have questions, go ahead and ask them. Feel free.
Welcome to Jeremy's IT Lab. This is a complete course for the CCNA, including everything you need to pass the exam, all 100% free. Make sure you stay tuned to the end of the video for the quiz to test your knowledge of the material in this video. Also, remember to download and use the Anki flashcards with the link in the description, which will help you very much in your studies. Let's get started. This is the 6th lesson in the series. In this lesson, we will continue with the same topic as in day 5, Ethernet LAN switching. But we will go a little deeper to make sure there aren't any holes in your knowledge. Once again, we're talking about sending traffic within a LAN, like between these 3 PCs in this small network here. The topic of how these PCs could send traffic out beyond the router to other networks is for a future lesson. Let's start locally first, with LAN switching. Before I get started, I want to speak a little bit more on Ethernet frames, which we talked about in the last video. The preamble and SFD is usually not considered part of the Ethernet header, although it is sent with every Ethernet frame. So the Ethernet header consists of these 3 fields: destination, source, and type. Therefore, the size of the Ethernet header plus trailer is 18 bytes if you don't include the preamble plus SFD. Now, there's also a minimum size for an Ethernet frame. The minimum size is 64 bytes, including the encapsulated payload, the packet. 64 bytes minus the 18 bytes of the header equals 46 bytes. Therefore, the minimum payload size is 46 bytes. Now, what if we send a payload packet that is less than 46 bytes? If the payload is less than 46 bytes, padding bytes are added, and these bytes are all zeros, by the way. For example, if you send a 34-byte packet, 12 bytes of padding will be added. Okay, that's all I wanted to add.
Okay.
Remember that the preamble and SFD might not be included as part of the Ethernet header, depending on how you define it, but they are included with every Ethernet frame. Also, remember the minimum size of the frame, 64 bytes, and that doesn't include the preamble and SFD, by the way. That means that the minimum payload is 46 bytes, and padding will be added if the payload is less than that. Now, let's get started with the main topics for today's video. So, here's the same small network we saw in the previous video. There are a couple changes, however. First, I changed the interfaces from fast Ethernet to gigabit Ethernet, hence the G00, G01, and G02 for each switch. Secondly, look at the MAC addresses. In the previous video, I used AAAA.AA00.0001 for PC1, or .0002 for PC2, etc. This time, let's use some more realistic MAC addresses. Notice once again that the OUI, the first half of a MAC address that identifies the maker of the device, is the same for each PC, 0C2F.B0.
Okay.
So that means that the PCs were all made by the same company. Of course, the second half of each device's MAC address is unique, since that represents the device itself. When I refer to these MAC addresses, I'll just use the last 4 digits to keep things simple. For example, I'll just say PC1's MAC address is 9D00, or PC2's MAC address is 6200. Now, let's add one more thing to this network topology. Let's add some IP addresses. We won't actually talk about the details of IP addresses in this video, but we'll need IP addresses to explain something else in this video. So this number here, 192.168.1.0/24, represents this whole network here. Then, .1 represents PC1's IP address. This is just the short version. PC1's real IP address is 192.168.1.1. PC2's IP address is 192.168.1.2. PC3's IP address is 192.168.1.3. And PC4's IP address is 192.168.1.4. Now, in the last video, I only really showed you part of the picture of how these PCs can communicate within this network. When a device sends some data to another device, it doesn't just include a source and destination MAC address. Encapsulated within that frame is an internet protocol known as IP packet, and that IP packet includes a source and destination IP address. For example, if PC1 wants to send data to PC3, the source IP will be 192.168.1.1, and the destination IP will be 192.168.1.3. The source MAC will be 0C2F.B011.9D00. However, PC1 doesn't actually know PC3's MAC address. when you send data to another computer, you enter the IP address, not the MAC address. So the user entered the IP address 192.168.1.3 as the destination, but PC1 has to discover PC3's MAC address by itself. Remember, these switches are layer 2 devices. They don't operate at layer 3, so they need to use MAC addresses, not IP addresses. So PC1 wants to send this Ethernet frame to PC3, but first it has to learn PC3's MAC address. To do so, it uses something called ARP, the Address Resolution Protocol.
Yeah, we kind of touched on this a little bit yesterday.
Let's take a look at ARP. ARP stands for Address Resolution Protocol. It is used to discover the layer 2 address, meaning the MAC address, of a known layer 3 address, meaning the IP address. For example, in our example here, PC1 knows PC3's layer 3 address, 192.168.1.3, but it doesn't know the layer 2 address, its MAC address yet. The ARP process consists of two messages: the ARP request, sent by the device that wants to know the MAC address of the other device, and the ARP reply, which is sent to inform the requesting device of the MAC address. In our example, PC1 would send the ARP request, and PC3 would send the ARP reply. The ARP request is sent as a broadcast Ethernet frame. Broadcast means it is sent to all hosts on the network. Because the layer 2 address of the destination host is unknown, it broadcasts the request and waits for a reply from the correct device.
Kind of like a flood.
The ARP reply is unicast. We learned about unicast frames in the last video.
Yes.
A unicast frame is sent to only one host. In this case, it's the host that sent the ARP request. Let's take a look at how this works on our network. Here at the bottom is the original frame that PC1 wants to send to PC3. But first, it has to send this frame. This is an ARP request frame. The source and destination
but
IP
it has been a
addresses,
while
as well as the
since
source
I've
MAC
done
address, are the
this
same.
because I
However, look at the
mainly
destination
build
MAC address.
computers.
FFFF.
I mainly build computers and do like help desk support currently right now, but we have to do when we connect printers and stuff, we have to put them on the right network. We have to put them in the right subnet and things. But I've also already taken CCNA 1, 2, and 3, so but that was like a year ago. So I should have taken my test a long time ago. I got busy. I wasn't able to do it, adulting and all that stuff, being an adult. So now I'm I just felt like it was the best course of action to start at the beginning and just review everything, then try to pick and choose and skip something. So I totally understand with the ARP that this is a layer 2 and that we're going from PC1 to PC3. So you can go to Cisco, and it's called Cisco Net Academy. Net Academy. I got you. Net Academy. And there are 3 courses that are recognized by just about everybody called CCNA 1, 2, and 3. There used to be a 4th one, but they kind of combined it into 3. And you can find an establishment that will teach it, or you can just sign up for them on your own through Net Academy, I believe. But I went to a junior college and signed up for cybersecurity path. That was the pathway, was cybersecurity, and a part of that pathway was CCNA 1, 2, and 3. So their classes, they're usually 8 weeks altogether. It goes really, really fast. Now, that also might just be an American thing. I think you said that you're from India. I have no idea how that would translate at all. But could be something for you to look into, because having a teacher and a mentor, it definitely helped knowing that I could email or talk to a teacher about, hey, what's going on with this, or things like that. Although the course was incredibly fast. And yeah.
.FFFF is the broadcast MAC address. This is the destination MAC address used when a device wants to send Ethernet frames to all other devices on the local network.
So this right here is the ARP request that's coming from PC1. I know I kind of talked through some of it. What's going on is that this is the source IP, this is the destination IP, and that helps us. But what we're really trying to do is figure out the MAC, because this is dealing with layer 2 stuff. To send out a broadcast, the MAC address is going to be all Fs. All those Fs mean that it's going to send out everywhere. And I believe it even comes back to the PC1 if I'm not mistaken. I know a flood sends it out everywhere except the sender. But either way, what matters is that it's going to send out everywhere saying, hey, are you this IP address, whatever, like here, we're looking for this PC, and it comes back and it says, yes, this is me.
So, PC1 has prepared the ARP request to be sent. It sends the frame out of its network interface, and it is received by switch 1. Switch 1 then adds PC1's MAC address to its MAC address table. When a MAC address is learned in this way, what is it called? It's called a dynamic MAC address,
Yes.
which we learned in the last video. So, since the destination MAC address is all Fs, switch 1 broadcasts the frame out of all of its interfaces, except the one it was received on. This is very much like what a switch does with an
Yeah, okay, so it doesn't receive it. It sends it everywhere except to itself, just like a flood.
unknown unicast frame, which we also learned about last video. It sends the frame out of G01 and G02, but not G00, because it received the frame on that interface. PC2 receives it, but it ignores the frame. That's because the destination IP address doesn't match PC2's IP address. So it knows that the ARP request is meant for a different PC, so it just ignores the request.
This has got to be a layer, with, especially now with like the way AI is and stuff, like this has got to be a security issue, because I could be a bet.
Cisco has a program called Virtual Internship Program conducted New York Cisco Networking Academy. I enrolled for that. I had to finish few of the courses from NetAcad.
Well, there you go. Because there could be a bad actor right here who could be spoofing the ARP. I wonder, he's not going to go on that. That goes far above what this video is, but it just makes me question it.
Of course, then switch 2 learns PC1's MAC address and adds it to the MAC address table, associating it with the G02 interface, since that's the interface the frame was received on. Since the destination MAC address is the broadcast MAC address, switch 2 also sends the frame out of all interfaces, except the one the frame was received on. So that means it sends the frame out of G00 and G01. PC4 ignores the frame because the destination IP address doesn't match its own. However, PC3 recognizes that the destination IP address does match its own IP address, so it doesn't ignore the ARP request. What it does is send the other ARP message I mentioned briefly, the ARP reply. Here you can see the ARP reply packet. The source IP is PC3's IP, and the destination is PC1's IP. The source MAC is PC3's MAC address, and the destination is PC.
So this switch thinks the interface that the MAC address of PC1 is this, because this switch can't see beyond this switch. Its job is to just get it to here. This job of this switch is to look and see the MAC address and be like, oh, it goes out this port. So that means as it... Yeah, I know ARP spoofing's a big deal, and it does come later. It just, when I see something like that, my brain just starts going, you know? Okay, so then he sends a thing. It goes this switch, comes out here. So when it comes back, we should know that its IP, its interface is going to be this one.
PC1's. Although the ARP request message was a broadcast message, because PC1's MAC address was used as the source MAC address of the ARP request message, PC3 now knows PC1's MAC address, so it can send the ARP reply directly to PC1, without having to broadcast the frame. PC3 sends the frame out of its network interface, and it is received by switch 2. Switch 2 learns PC3's MAC address, and enters it into the MAC address table, associating it with the G00 interface. Since this is a unicast frame, and switch 2 already has an entry for the destination MAC address in its MAC address table, what kind of frame is this, and what does switch 2 do with it? It's a known replies have a source of PC3.
We're
replies
we're
have a
going
source
bald.
of PC3. Replies have a source of PC3. Replies have a source of PC. Replies have a source of PC3.
Whoa, I don't know what that was. What? Oh, my stupid cat. Okay, hold on. Where? His tail. Oh my gosh, dude. Oh, stop it. I don't have a lot of time, boy.
Cast frame or a broadcast frame. Because switch 2 learned PC1's MAC address on the G02 interface, it will send the frame out of that interface towards switch 1. Switch 1 receives the frame, and since it has already learned PC1's MAC address on the G00 interface, it simply forwards the frame out of the interface, and PC1 finally receives the ARP reply. PC1 will then use that information to add an entry for PC3 to its...
Well, I was a teacher. I just wasn't an English teacher. I was actually a band director, and then I was a graphic design and animation teacher, and then now I do IT. But still teacher nonetheless. Okay, so we went over here. GT, the gigabyte 2. Yes, so I was correct. So all this switch knows is that this PC's interface is this.
ARP table, which is used to store these IP address to MAC address associations. Let's take a look at an ARP table. This is a screenshot of part of the ARP table from my PC. I use Windows on my PC, but you can use the ARP-A command to view the ARP table, whether you run Windows, Mac OS, or Linux on your computer. The Internet address column displays IP addresses. The physical address column displays the MAC addresses that correspond to the IP addresses. If the type column displays static, it means that it is a default entry. It wasn't actually learned by sending an ARP request. However, if the type column displays dynamic, that means that the entry was learned by sending
I really feel like I need to watch this all one more time. I'm sorry, guys. I just need to watch this ARP reply one more time.
What company you are working for right now?
No, I'm not going to disclose that information.
Here you can see the ARP reply packet. The source IP is PC3's IP, and the destination is PC1's IP. The source MAC is PC3's MAC address, and the destination is PC1's. Although the ARP request message was a broadcast message, because PC1's MAC address was used as the source MAC address of the ARP request message, PC3 now knows PC1's MAC address, so it can send the ARP reply directly to PC1, without having to broadcast the frame. PC3 sends the frame out of its network interface, and it is received by Switch 2. Switch 2 learns PC3's MAC address and enters it into the MAC address table, associating it with the G00 interface. Since this is a unicast frame, and Switch 2 already has an entry for the destination MAC address in its MAC address table, what kind of frame is this, and what does Switch 2 do with it? It's a known unicast frame, and Switch 2 will simply forward it out of the interface in the MAC address table. It will not flood it like an unknown unicast frame or a broadcast frame.
Because that switch
Because Switch 2
already
learned
knows
PC1's
where
MAC
that
address
MAC
on the
address
G02
is.
interface, it will send the frame out of that interface
If that switch didn't know where that MAC address was and it wasn't on its ARP table already, it would have flooded it.
towards Switch 1. Switch 1 receives the frame, and since it has already learned PC1's MAC address on the G0...
So that means that whenever you first hook up switches, there's a lot of traffic that's going on, because these switches aren't going to know where all these PCs are. And the best thing probably, I would imagine, is to have every PC or every device ping every other device, just so that way it has an idea of where it's at. That might not be fully realistic in terms of like a big setup, but for a small setup, that would make sense to me. Well, and honestly, so what if there's a lot of traffic? Like, it only happens once, so maybe that's not necessary.
00 interface, it simply forwards the frame out of the interface, and PC1 finally receives the ARP reply. PC1 will then use that information to add an entry for PC3 to its ARP table, which is used to store these IP address to MAC address associations. Let's take a look at an ARP table. This is a screenshot of part of the ARP table from my PC. I use Windows on my PC, but you can use the ARP-A command to view the ARP table, whether you run Windows, Mac OS, or Linux on your computer. The Internet address column displays IP addresses. The physical address column displays the MAC addresses that correspond to the IP addresses. If the type column displays static, it means that it is a default entry. It wasn't actually learned by sending an ARP request. However, if the type column displays dynamic, that means that the entry was learned by sending an ARP request and receiving an ARP reply.
Thanks, man.
You can see one entry like that here, with an IP address of 192.168.0.1 and its MAC address next to it. That's the address of my home router, by the way. My PC used ARP to learn the MAC address of the router. Now let's take a deeper look at the MAC address table that is kept on these switches, and some additional information. I recreated the same topology in the network emulator software, GNS3. GNS3 is similar to Packet Tracer in that it allows you to create networks and practice configurations on Cisco devices, but it's also different in some key ways. Packet Tracer is a network simulator. It's a piece of software designed to simulate the operation of a real network. GNS3, however, runs actual Cisco iOS software, so these are real Cisco switches running virtually. However, GNS3 requires you to purchase your own copies of Cisco iOS. So although GNS3 itself is free, using Cisco iOS with GNS3 is not. That's why I choose to use Packet Tracer for the lab videos in this series. It's totally free, and it lets you practice just about everything you need.
So
for
Packet
the CCNA.
Tracer is the free version.
I also want to show you GNS3 sometimes in these videos, however, since you probably want to use it later as you progress in your networking studies. Don't worry about using GNS3 for now, though, unless you really want to try it out. You can get it at gns3.com. So here's our topology, and notice this magnifying glass here. This is a cool feature of GNS3.
Emulation is
It
so
integrates with
crazy.
another piece of software called Wireshark, and we'll use it to analyze exactly what traffic passes between PC1 and Switch 1. I'm going to send a ping from PC1 to PC3. The process is the same, but let me just run down one more time what happens. Just like our example before, PC1 doesn't know the destination MAC address, so it has to send an ARP request. The ARP request is sent to all other hosts on the network. PC3 responds to the ARP request, since its IP address matches the destination IP address in the ARP request. PC1 then learns the MAC address of PC3, adds it to its ARP table, and uses that information to add the destination MAC address to the ping it wants to send. Now, before I move on, you may have heard of ping before, but let me explain how it works. Ping is something you're going to be using a lot. It's a network utility that is used to test reachability, for example, to test if two computers can reach each other. It measures the round-trip time, for example, the time from PC1 to PC3, then back to PC1. Much like ARP, ping uses two messages, ICMP echo request and ICMP echo reply. Again, this is similar to an ARP request and ARP reply. However, the PC won't broadcast the ICMP echo request. It is sent to a specific host. So it has to know the MAC address of the destination host, which is why ARP must be used first. The command to use ping is ping, followed by the IP address you want to ping to. For example, 192.168.1.3 for PC3 in our network. Let's take a look at the ping process. So I'm on PC1 here. Note that...
Is that why sometimes when you ping, it won't work, everything will work except for the very last one, and then you'll do it again, and then all of a sudden it works?
This is actually the Cisco iOS CLI. I'm using Cisco routers to simulate PCs, since it's easier than setting up virtual PCs to ping in GNS3. I use the command ping 192.168.1.3 to send an ICMP echo request to PC3. Take a look at this message here, sending 5 100-byte ICMP echoes to 192.168.1.3. By default, a ping in Cisco iOS sends 5 ICMP echo requests, and then you should get 5 ICMP echo replies back. And the default size of each ping is 100 bytes. The period indicates a failed ping, and the exclamation points indicate a successful ping. As it says here, success rate is 80%, 4 out of 5. It also shows the round-trip time, giving the minimum, average, and maximum time of the 4 successful pings. Now, why did that first ping fail? Well, that's because of ARP. PC1 didn't know the destination MAC address, so it had to use ARP, and in that time, the first ping failed. After PC1 learned PC3's MAC address, however...
it is correct. So I am correct. So when you ping something the first time and, you get 3 out of the 4 good, is because it was handling ARP and it was doing other things. And then when you do it again, it usually is successful. So that's why it's good to do it 2 or 3 times just to double check.
The ping succeeded.
Especially if it almost went through.
Let's take a quick look at the ARP table here. The command for Windows, macOS, and Linux was ARP-A. However, in Cisco iOS, it's show ARP from privileged exec mode. Here's the ARP table. Notice there is an entry for 192.168.1.1, which is PC1 itself, and then below it, 192.168.1.3, which is PC3. This is a screenshot from Wireshark, which I mentioned earlier. Wireshark allows you to perform what are called packet captures to analyze the contents of network traffic. Notice the protocol column, ARP, followed by ICMP, which is ping. Here's the first ARP packet. The source MAC is 0C2F B011-9D00, which is PC1's MAC. The destination is broadcast, which is all Fs. Look at the info on the end. Who has 192.168.1.3? Tell 192.168.1.1. This describes what the purpose of ARP is. The ARP request is asking which MAC address has an IP address of 192.168.1.3, and to send a reply to itself, 192.168.1.1.
Interesting.
Next is the ARP reply. The source address is 0C2F B06A3900, PC3's MAC, and the destination is PC1's MAC. Look at the info section again here. 192.168.1.3 is at 0C2F B06A3900. It's telling PC1 its MAC address. After that, there are 4 ICMP echo requests and 4 ICMP echo replies. Note that the ICMP echo requests have a source IP of PC1 and destination of PC3,
wow, just
and the
pinged it a
ICMP
bunch
echo
of
replies
times,
have a source of PC3
and it worked.
and destination of PC1. I'll use Wireshark at various points throughout this course, but I think you can see how useful it can be in analyzing networks.
Yeah. Well,
Okay,
that was really
hopefully you understand this process a little better now. Basically, if device A wants to send traffic to device B, which is on the same network, device A first has to use ARP to learn device B's MAC address.
Yes.
And then it can send traffic to device B. Now let's finally take a look at the MAC address table on a Cisco switch. Here it is. This is the command to view it. Show MAC space address hyphen table. Old versions of Cisco iOS use show MAC hyphen address hyphen table, but newer versions got rid of the first hyphen, and now it's this, show MAC space address hyphen table. Now let's look at each section of the MAC address table. Before, I only showed the MAC address and interface. First is the VLAN. VLAN means virtual local area network. We'll learn about those later, but as is displayed here, the default is 1. Next is the MAC address column. You can see PC1 up top and PC3 on the bottom. Next is the type. Remember what I said about dynamic MAC addresses? Well, it is displayed in the MAC address table as well. Both of these MAC addresses were learned dynamically. I did not manually configure them on the switch.
Oh, wow.
Finally, ports, which is another word for interfaces. So you can see that this matches the small MAC address table I put here in this diagram earlier. Here's the entry for PC1, and here's the entry to PC3. Now, I mentioned in the previous video that these dynamic MAC addresses are removed from the MAC address table after 5 minutes. This is known as aging. If the switch doesn't get any traffic from that MAC address for 5 minutes, it will remove the entry from the MAC address table. However, you can also manually remove MAC addresses from the table. Here I use the show MAC address table command, and you can see the entries for PC1 and PC3. Then I use the command clear
because
MAC
otherwise
address
your
table
MAC
dynamic.
address table would just
As you can
get
see,
huge
all of the dynamic MAC addresses have been removed.
and would be filled
Remember this
with
command.
like crap that
Clear MAC address table dynamic.
you don't use anymore.
Now, if you don't want to clear all of the MAC addresses from the table, you can add some additional options to the command. Once again, I used show MAC address table, and you can see both entries for PC1 and PC3. This time I used a different command, clear MAC address table dynamic address, followed by PC1's MAC address. Then if I use show MAC address table again, only PC3's MAC address can be seen. Here's the command once more. Clear MAC address table dynamic address, then the MAC address. Finally, one more option to clear the MAC address table. Again, show MAC address table shows both PC1 and PC3's MAC addresses. This time I use the command clear MAC address table dynamic interface, followed by gigabit Ethernet 00. This clears all MAC address table entries for a specific interface. As you can see, once again PC1's MAC address is removed, because it is connected to the G00 interface. Here's the command again. Clear MAC address table dynamic interface, and then the interface. Before we move on to the quiz, I want to show you a little more in Wireshark regarding what I said in the beginning of this video about the Ethernet frame. In this packet capture, I sent a 36-byte ping with the command ping 192.168.1.3 size 36. First, notice the type field down here. As I mentioned in the last video, IPv4's Ethernet type is 0x0800. The 0x just means that it is using hexadecimal, so really it's 0800. Next, look at the padding here. Remember, the minimum payload size for an Ethernet frame is 46 bytes.
Yeah, 46 bytes.
And I sent 36 byte pings, so there should be 10 bytes of padding. These zeros are hexadecimal zeros. Each hexadecimal digit is 4 bits, so 2 digits equals 8 bits, or 1 byte. If you count the zeros, there are 20 zeros, so that means 10 bytes of padding. If I zoom out a bit,
because it
you can also
has
see
to
the
be
padding
that
down
size.
here. These 10 pairs of zeros are the 10 bytes of padding added to the 36-byte ping to make them meet the 46-byte payload minimum size. One last thing in Wireshark, this time looking at ARP. Remember, the IPv4 Ethernet type is 0800, and the IPv6 Ethernet type is 86DD. As you can see here, the ARP Ethernet type is 0806. This indicates that an ARP packet is inside of this Ethernet frame. Okay, so we covered a lot of important stuff in this video.
Wow, that was a lot of information.
We talked about some more details of the Ethernet frame, including the minimum size of the Ethernet payload, which is 46 bytes. We talked about ARP, the address resolution protocol. It is used to learn the MAC address of a device, for which you already know the IP address.
There was a lot of information
It uses
in
two
this
messages,
video.
an ARP request, which is broadcast to all devices on the local network, and an ARP reply, which is sent to the device which sent the
Really,
request.
the payload size is
We
what
also looked
got
at
me.
the ARP table on a Windows device and a Cisco iOS device. We talked about ping, which is used to test reachability in a network. It also uses two messages, ICMP echo request and ICMP echo reply. Finally, we looked at the MAC address table on a Cisco switch, including how to clear it in a few ways.
Really, it's the payload.
Let's move on to the quiz
size
for today's
and how
video.
that works.
Here's question 1.
Definitely made a lot of things
You
click.
send a 36-byte ping to another computer and perform a packet capture to analyze the network traffic. You notice a long series of bytes of 00000000 at the end of the Ethernet payload. How can you explain these zeros?
Padding.
Pings are a series of zeros. B, they are padding bytes. Or C, they are the Ethernet FCS. Pause the video to think about your answer.
They're padding bytes. We
The
just
answer is
learned
B,
that.
they are padding bytes. The ping you sent was 36 bytes, but the minimum Ethernet payload is 46 bytes, so a series of padding bytes must be added to meet the minimum payload size. Let's go to question 2. Which of these messages is sent to all hosts on the local network? A, ARP request. B, ARP reply. C, ICMP echo request. Or D, ICMP echo reply. Pause the video to think about your answer.
Wait, which of these messages is sent to all hosts on a local network? An ARP request.
The answer is A, ARP request. Let's check.
Nailed
The ARP
it.
reply message is a unicast message sent to the host that sent the ARP request. So B, ARP reply is incorrect. The ICMP echo request is a unicast message used to test the reachability of another specific host. The ICMP echo reply is a unicast reply to the request. So C, ICMP echo request, and D, ICMP echo reply, the two messages used in ping, are incorrect. The ARP request message is used to learn the layer 2 address of a host. Because the layer 2 address is not yet known, the message has to be broadcast to all hosts on the local network. So A, ARP request, is the correct answer. Let's go to question 3. Which fields are present in the output of the show MAC address table command on a Cisco switch? A, MAC address and ports. B, VLAN, MAC address and ports. C, VLAN, MAC address, type, and ports.
I think it's B.
D, internet address, physical address, and type. Pause the video to think about your answer.
Either B or D. I think it gives the VLAN.
The answer is C, VLAN, MAC address, type, and ports.
And it gives the type.
Let's take a look. Here is a screenshot of the MAC address table on a Cisco switch.
Oh, that, yes.
Notice the 4 fields: VLAN, MAC address, type, and ports. So C is the correct answer. By the way, answer D, internet address, physical address, and type, is the output shown from the ARP-A command on my Windows PC.
Yeah.
This is part of the ARP table on my PC, not the MAC address table on a Cisco switch. Let's go to question 4. Which types of frames does a switch send out of all interfaces, except the one the frame was received on? A, broadcast and unknown unicast. B, broadcast and known unicast. C, known unicast and unknown unicast. Or D, broadcast, unknown unicast, and known unicast. Pause the video to think about your answer.
Because it's a broadcast, but it knows where
The
it's
answer
going
is A,
from.
broadcast and unknown unicast. Let's
What?
check. Known unicast frames are sent to a single host. Because the switch already has an entry for the destination in its MAC address table, there is no need to flood the frame out of all interfaces. So B, C, and D are incorrect because they include known unicast. Broadcast frames have a destination address of ffff.ffff.fffff and are sent to all hosts on the local network. Unknown unicast frames are destined for a single host. However, the switch doesn't have an entry for the destination in its MAC address table.
Oh,
so it must
I
flood.
thought it was like broadcast because it was sending it, and then a unicast because it was replying back to it. I thought that's what it meant.
Of the frame. So A, broadcast and unknown unicast, is the correct answer. Let's go to the last question for today's video. Which command is used on a Cisco switch to clear all dynamic MAC addresses on a specific interface from the MAC address table? A, clear MAC address -table interface ID. B, clear MAC address table dynamic interface ID. C, clear MAC address table dynamic interface ID.
We don't need this.
Or D, clear MAC address table
This is it. It's D.
dynamic interface ID. Pause the video to think about
Because
your
we're
answer.
trying to clear all dynamic MAC addresses.
The answer is D, clear MAC address table dynamic interface ID.
And remember that a hyphen means that in the eyes of the Cisco switch or the router, that this is one word. That's why that's why they use hyphens. So that way this is one word.
Make sure to spend time doing practice labs in Packet Tracer to help you remember the commands. That's all for the quiz. Once again, there will be supplementary materials to help you study.
We're going to do the packet tracer
As always,
next.
there will be Anki flashcards to help you remember what you learned.
And we're going to do the flashcards.
There will also be a Packet Tracer practice lab to give you some hands-on experience with Cisco devices. Good luck with your studies. Thank you for watching. Please
If
subscribe
you're not
to the channel,
already, you
like
should
the video,
definitely
leave a
subscribe
comment,
to
and share the
Jeremy's
video with
Tech
anyone
Lab.
else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.
Hey, leave him alone.
Welcome to Jeremy's IT Lab. This is a free complete
God, he's
course
so
for
slow.
the CCNA 200-301. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. Let's get started. In this lab, you'll practice and develop your understanding of some of the concepts learned in the Day 5 and Day 6 videos on Ethernet LAN switching. As you can see, the network topology we will use in this lab is like the example network I used in those previous lecture videos, with 2 switches, each with 2 PCs connected to them. Let's get started and go through the steps.
All right, let's see if we can do it by ourselves and then use the video if we need it. So if PC1 pings PC3, what message will be sent over the network and which device will receive them? So if we go here, config terminal, and we go to ping 192.168.1.3 3. Why? What? There we go. Hit the wrong one. Ping 192.168.1.3. Okay, so we made it. We got it. So send the ping and use packet tracer simulation mode. Oh, simulation mode. Okay, well, let's resend that. That was it. That's all we get. There we go. There we go. So we made it here. Switch 1, switch 2. I wonder if the fact that I already pinged it once messed with it. Okay. Interesting. Okay. See what he did.
First off, there is a note saying that both switches have an empty MAC address table, and all PCs have an empty ARP table. Keep that in mind as you try to answer step 1, which asks us, if PC1 pings to PC3, what messages will be sent over the network and which devices will receive them. So, if PC1 wants to send a ping to PC3, it has to know PC3's MAC address. We can type ping 192.168.1.3 on PC1 to send a ping, but until PC1 knows PC3's MAC address, it can't send the ping. That means PC1 will have to send an ARP request. So that's the first message. Now, which devices will receive the ARP request? Well, the ARP request is a broadcast message, so all devices on the local network will receive it, except for PC1, of course, which sends the message. PC2 and PC4 will ignore the message, but then PC3 will send an ARP reply, which is the second message. Unlike the ARP request, which is a broadcast message, the ARP reply is a unicast message, so the message will be sent through switch 2 and switch 1, and then be received by PC1 only. No copies of the message will be sent to PC2 or PC4. Then, PC1 will be able to add PC3's MAC address to its ARP table, and use that information as the destination address of its ping. So, the third message that will be sent is an ICMP echo request from PC1. This is a unicast message.
Oh, all of these are the different messages that are going. It's just going really, really slow, so that way you can see it.
That will be received by PC3 only. Then, PC3 will send an ICMP echo reply, which is also a unicast message that will be received by PC1 only, after passing through switch 2 and switch 1, of course. So that's it. Those are the messages that will be sent over the network if PC1 pings PC3. Now, there won't be just one ping. PC1 will send multiple pings, 4 by default from a Windows PC. Step 2 asks us to send a ping and use Packet Tracer's simulation mode to verify our answer. First, let me click on simulation mode here in the bottom right. Then, to send a ping from a PC in Packet Tracer, click on the PC, click on desktop, and click on command prompt. Now just type in the command. PC3's IP address is 192.168.1.3, so the command is ping 192.168.1.3. Immediately, you can see that both an ICMP message, which is the ping, and an ARP message appear. I'll click on the ICMP message, and then click on layer 2. Look at the info here. The next
Mine
hop
didn't do that
address
because
is
I
a
pinged
unicast.
it before it.
The ARP process looks it up in the ARP table, but the next hop IP address is not in the ARP table.
How do you...
The ARP process looks at and an ARP message appear. I'll click on the ICMP message, and then
Okay.
click on layer 2. Look at the info here. The next hop address is a unicast. The ARP process looks it up in the ARP table, but the next hop IP address is not in the ARP table. The ARP process tries to send an ARP request for that IP address and buffers this packet. Buffers means it holds the packet, so it can send it later. Now let's click on the ARP message and look here at the information. This time I'll click on Outbound PDU Details, which shows us detailed information about the frame. Do you recognize these fields? Preamble, SFD, destination address, source address, type, data, which is the encapsulated packet, and then FCS.
How come mine's not saying ARP? Oh, there it is. It's doing it. There it is. And look, it just did it. That's so dope. Yep, there it is. That's the broadcast. These are all of it for PC1 because of the broadcast. That's so much information, man. And now it knows. That's wild. And there it's moving. Okay. What's the next question? We'll let him finish talking in a second. Use the pings to generate the network traffic and allow switches to learn the MAC addresses of all the PCs. Use show command on the switch to identify the MAC address on each PC, then clear it. Okay, so we gotta wait for this bad boy to run its course.
If you watched my last 2 videos, you should recognize all of these fields of the Ethernet header and trailer. Notice in particular the type field of 0806, which indicates ARP, and the destination MAC address of all Fs, which is the broadcast address.
Whoa, so I can break down the actual packet? I didn't know you could do that. Whoa. This is crazy. There's the preamble. And this is telling you the bytes. Wow. I had no idea. And there's the source. PDU format. Wow, hold on. I'm just kind of taking this all in for a second. I didn't know that this was there. There's the type. Wow, that's like super helpful. It's like really helpful, actually.
Okay, now I'll exit from here and click through the process. The ARP reaches switch 1, is broadcast to PC2 and switch 2, and then broadcast to PC3 and PC4. Only PC3 replies, this time with a unicast message, which arrives at switch 2, then switch 1, and then PC1. PC1 can then finally send its ICMP echo request, which is unicast and goes to switch 1, switch 2, and then PC3. PC3 then sends the ICMP echo reply back through switch 2, switch 1, and then arriving at PC1. I'll just press this play button, and you can see the rest of the pings being sent between PC1 and PC3. There should be 4 in total, as these packet tracer PCs operate like Windows PCs. Cisco devices, however, send 5 pings by default. Now, step 3 tells us to generate network traffic and allow the switches to learn all MAC addresses of the PCs on the network. Remember, switches dynamically learn and enter MAC addresses into their MAC address table by looking at the source address field of frames they receive. So since we just pinged between PC1 and PC3, both switches should know their MAC addresses. But just in case, I'll switch back to real-time mode and send one more ping from PC1 to PC3, because sometimes Packet Tracer has problems with simulation mode. Okay, next, let's send a ping from PC2 to PC4 so that the switches can learn their MAC addresses. I'll go on PC2. And now I'll ping PC4. Ping 192.168.1.4. Step 4 asks us to use show commands on the switches to identify the MAC address of each PC. Because the interface each PC is connected to is displayed on the network diagram, if we look for that interface in the MAC address table, we will be able to identify the MAC address of each PC. I'll go on switch 1. We have to be in privileged exec mode to view the MAC address table. So use the command enable, or just en. The command to view the MAC address table is show MAC space address hyphen table. Make sure you don't mix up the space and hyphen. Okay, first of all, let's find PC1, which is attached to the fast Ethernet 01 interface. Here it is, and you can see the MAC address
What?
here. Note that the MAC address in your lab may be different. I'm not sure if Packet Tracer keeps the MAC addresses consistent if you load the labs up on another computer. How about PC2?
Okay, hold on. I definitely pinged all this crap. I definitely did it all, so how come it's not there? Oh, he said... So maybe... Okay. Let's just ping them all real quick. Okay. There it is. So he said that sometimes it has a little trouble in simulation mode. It did. Okay, and then there's my MAC addresses. Okay, and then now I need to get rid of it, which I do not remember what that is.
Well, it's connected to fast Ethernet 02, so here is PC2's MAC address. Now, as for PC3 and PC4, we have a problem. Switch 1 only knows that it can reach these two MAC addresses via gigabit Ethernet 01. Just by looking at this MAC table, we don't know which address belongs to PC3 and which belongs to PC4. So let's go on to switch 2. Once again, I'll enter privileged exec mode, enable. Now let's view the MAC address table. Show MAC address table. PC3 is connected to fast Ethernet 01, so this must be its MAC address. And PC4 is connected to fast Ethernet 02, so this must be its MAC address. We have successfully used the show MAC address table command to identify the MAC address of each PC. Now let's do step 5, which is to clear the dynamic MAC addresses from the MAC address table of each switch. Since I'm already on switch 2, I'll start here. The command is clear MAC address table dynamic. But before I hit enter, I want to show you something. I'll use the question mark, which is also known as context-sensitive help. As you can see, it doesn't display any additional options here. If you remember from the Day 6 lecture video, when I did the demonstration in GNS3, I could clear specific MAC addresses by specifying the address or interface. Packet Tracer, however, does not support this option. You have to clear all MAC addresses. So I enter the command, then I'll use the up arrow on the keyboard to go back to the show MAC address table command. Enter it once more, and you can see the MAC address table is now empty.
Well, hold on. What did I do wrong? Oh, I put remove, not clear. Dummy. Done. And now they're all gone. Wow, okay. That was,
I'll do the same on switch 1. Clear MAC address table dynamic. Press the up arrow twice to go back to the show MAC address table command. Hit enter, and there we go. The address table is now empty. We have successfully completed this lab. Thank you for watching.
If you're not subscribed to Jeremy's IT lab, you definitely should be. He is really, really good. No, I do not want to save. Definitely do not want to save. I'm kind of out of time, so we're going to have to do the Anki cards next time. But next Tuesday is probably going to be a little bit of a longer stream. If you'll notice, a lot of times when I'm studying, I start out kind of small because I'm trying to like learn and figure out the flow of it and things like that. Right now we're doing an hour, maybe 2 hours. Probably by the end of the month, we'll probably be doing 3 to 5 hours, just depending on like what's going on that I have personally going on throughout the day, and then knocking out stuff. So that way we're not just doing one lesson every single day. We'll do one new lesson and then review like the last 2 lessons, so that way it stays fresh in our head. That's the idea, what we want to do. So thank you guys for checking out, coming and hanging out with stuff. Appreciate it. Next Tuesday, we're going to study again at 8 a.m. I might bump it up to 7:30 to kind of help us out with a little bit more time, depending on what's going on. But you can follow me on Instagram, Tyler Lemmond. If you are here with the Paradiddle Pete channel, thanks for coming over to Tyler Lemmond Tech channel. And if you're interested in any of the gaming stuff that I do, that's going to be on the gaming channel tomorrow at 8 p.m. I don't know if we're going to finish High on Life 2. It kind of sucked. But anyway, that's what's going on. If there's no other questions or anything like that, I'm going to get out of here because I got to take care of a few errands and stuff like that. Remember, wait, where is it? Hold on. I got to pull it up. It's important. It's important. It's important. Like and subscribe. Work with what you got. Always work with what you got. Build what you need. Like, subscribe, all that good stuff. There's videos here for you if you want them. More videos are on their way. All right, I'm out.